So good evening, everyone. Welcome to a special Earth Day edition of Science at the Theater, sponsored by the Friends of Berkeley Lab. My name is Jeff Miller, Head of Public Affairs at the lab. How hot will it get? That's the answer that we're all looking for, right? That's why you've turned out in such large numbers. What does a rapidly warming planet mean to our future? Tonight we have 5 panelists who will help answer that question. 4 of the 5, Bill Collins, Margaret Torn, Michael Wehner, and Jeff Chambers, are Berkeley Lab scientists. Our 5th panelist, Max Aufhammer, is based at UC Berkeley. Now, I'm not going to sugarcoat this. The news they are about to share is not good. But we think that as scientists working in the public interest, that's for all of you, with public funds, that's also about you, we have a responsibility to tell you what we have learned. And because Berkeley Lab exists to bring science solutions to the world, we hope that what we learn will lead to discoveries that benefit everyone. With that, please welcome our first presenter for the evening, Bill Collins, who is the Director and Chair of our Climate Sciences Department at Berkeley Lab. Thank you.
Thank you very much for coming out for this event on Earth Day. We are going to step through a bunch of science that we do at the laboratory that concerns how the climate works now and how it might work in the future. And my job at the beginning of this evening is to tell you about what's coming based upon what's happened in the past. So I'm going to talk to you about what the future may hold based upon our best ability to predict it using some of the most advanced climate models on the planet. These models have been developed by a very large community, and they essentially provide us with our crystal ball for how the climate might change. They're not Excel spreadsheets. They're a lot more complicated than that. They're based upon our best knowledge about how fluids work, how the atmosphere and how the ocean work, and how processes within the climate system, including winds, waves, clouds, plants, how all of those interact to create the Earth system. So this is really, these models are really a synthesis of our knowledge about how climate works now, and we hope that those principles will carry forward so that we can extrapolate into the future. These models are now capable of simulating climate features as small as the currents in the ocean, down to scales of 10 kilometers or less. So we really have quite a lot of capability to look at the climate and then to ask how it will change in the future. This has been made possible thanks to some really remarkable advances in computer technology. And I've used a scale here. This is unfortunately, I realized as I was looking at my slide this afternoon and practicing, I thought, I'm not sure if scientific notation is probably the best choice. So I'll step you through what these units mean. 1.e plus 0.6 is a million, and then you go up to a billion with the 9. And then I think what comes next is a trillion with 12, quintillion at 15, and so forth. We've experienced a billion-fold increase in computing power since climate science began in the late 60s, early 1970s. Your iPad 2 is as powerful as one of the supercomputers on this figure that cost $20 million in the early 1990s. It's really quite a revolution in our ability to synthesize information and to also use that information then to project what might happen as we continue to add greenhouse gases to the Earth's atmosphere. These models have really become extraordinarily powerful. We can, as I mentioned earlier, simulate climate change down just barely to the scale of San Francisco County, which is approximately 10 to 11 kilometers on a side. These are results from a recent simulation that we did with a model that we've all been developing jointly between the Department of Energy and the National Science Foundation. What's shown here is water. And water really plays a central role in the climate system. It's actually the most important greenhouse gas. Of course, it's the source of the water that we drink, the rain on which we depend, the rivers, the oceans. Understanding how water moves through the climate system is really a critical challenge for us. And you'll hear a little bit later from Mike Wehner about how water and climate change might interact to create more extreme weather. The other chemical species in the climate system that's particularly critical is carbon dioxide. And we'll hear from Margaret Torn and also from Jeff Chambers about how carbon dioxide, of course that's a critical compound for the greenhouse gas, but it's also a critical compound for the development of plant life on Earth, how that compound interacts with climate change and with the living world around us. And so we'll be hearing about all these topics from speakers who are coming up just after me. My job is to sort of set the stage for why we're concerned about this topic. And a lot of this science is being done by very large teams. So you're seeing 5 of us here from Berkeley Laboratory, and several of us also work at Cal. But we do this science in the context of a very large and a very energetic international community. I wanted to describe that process to you briefly so you understand how the science is accumulated both at the local, national, and also at the international level. We just recently had a meeting of a process called the Intergovernmental Panel on Climate Change. And this is a group that was convened by the United Nations Environmental Program. It's met 4 times in the past, and it's having its 5th grand round of meetings now. Michael, Max, and I are all part of that report and are contributing to it. The reason I'm mentioning this to you will become evident in a second, but this is our meeting of 270 people writing the first working group report. That report will be approved in September of this year, and then will become enter the public domain in January of 2014. So it's coming up soon. For some reason, IPCC likes to maximize our carbon footprint. I'm not really quite sure why, but we met in Hobart, Australia, which is a long way from here, I can assure you. Spent a lot of quality time on the plane reading and rereading various reports. We met there partly because there were so many authors on that team, and also partly because this is a launching point for a lot of Australia's work looking at the Antarctic. But the other distinctive thing about this is that we went there during summer of 2012 and 2013. This was an exceptionally hot summer in Australia. The Australian government issued a report after we were there called the Angry Summer of 2012-2013. 123 records broken in 90 days. This is the heat index. I'm not sure if you can see it, but the bright orange and yellow colors indicate regions of high fire danger. Significant expansion of fire danger while we were there. Huge fires. This is a fire that was happening in Tasmania just before we arrived. If I can get this slide to transition. Here's this is a picture of a beach. There's a little girl over here playing, in the ocean while huge fires combust behind her. The day that we returned home through Sydney, it was 120 degrees Fahrenheit in Sydney. Some of the planes were unable to take off because their skin was buckling in the heat. It was pretty extreme. Okay, so that's what's happening now. And let me show you what's been happening in the past, and then what we'll do is we'll use a climate model or a set of climate models to look forward. So I'm now going to summarize for you what's been happening recently, and then we'll use that sort of crystal ball feature of the climate models to look forward. So this is climate change. This is a very nice animation. It's 60 years of climate change in 13 seconds from NASA. And what we're looking at is the anomaly, or the difference in temperature relative to climatology. So the scale actually runs, it goes from -2 degrees Celsius if you're cooler than normal, up to +2 degrees Celsius if you're hotter than normal. We wind up in 2012, and we're in the hottest year ever experienced in the United States. Most of the central part of the country experienced temperatures that they have not experienced since the start of records kept by the National Climate Data Center. So totally unprecedented, very unusual year. So what's going to happen in the future? Now at this point, I have to step you through three slides with some graphs, so bear with me. I'll try to make this tolerable. But this is the way that scientists look at this, and so I thought I would share it with you. And the storyline here is that the more we emit, the more carbon dioxide that humans emit, the higher the concentration of carbon dioxide in the atmosphere. That's the message of this slide. And the next slide will show you the relationship between those higher concentrations and higher temperatures, and then I'll show you the spatial patterns of those temperatures in the third slide. So that's what's coming. The reason why this figure is important is that we had to actually sort of hedge our bets about what the future might hold. So here we are at 2013, and at this point we branch off 3 different projections for where humanity might go. Sort of continuing basically with no policy, that's this blue curve, and then several other curves where we anticipate some imposition of policy to draw down carbon dioxide. The thing I want to show you is that the higher the emissions, the higher the concentrations of carbon dioxide. So this is concentrations of CO2. I need to sort of normalize this graph for you so you understand what the units mean. Off the bottom part of this axis at 270 parts per million is the concentration that we had up until the introduction of the steam engine for the last 10,000 years. So 270 parts per million is where we started at the beginning of industrialization. We're now at a concentration, 390 parts per million, that was last experienced by the climate system naturally 3 million years ago. So at the launch of the major period of glaciation that's occurred since then. And if you look at these figures, I just want to, I think it's quite remarkable. As we go forward in time, this blue curve, the one with no policy, hits 700 parts per million, cruises right through. The last time the Earth experienced 750 parts per million was 34 million years ago, at the dawn of the creation of Antarctica. And so we actually have invented a time machine. It's called your car engine. And that car engine, your car engine, mine, everybody else's, is taking us back in time, back in fossil time, to periods that we have not experienced since the, really since the advent of our mammalian ancestors. So spooling forward now in time, if you trace these concentrations, you can and look at how they relate to increased temperatures, they match 1 to 1. The higher the emissions, the higher the concentrations, the higher the concentrations, the higher the resulting temperature. And these temperatures, especially for no policy, reach 8 degrees Celsius, roughly, let me see if I can do roughly 15 degrees Fahrenheit, so really quite toasty compared to present day. That's globally global mean change. And if we look at the patterns, I think it's quite interesting to see what those imply. Let's consider 2 time periods. The near term, 2015 to 2035, so 1 generation away. And then at the end of the century. Let's start with the end of the century, and again, going from top to bottom, we have a sort of the Bill McKibben world, where you hit 360 parts per million, just a little bit higher than its 350 parts per million. So let's call this Bill McKibben world. And you know, it changes by a bit, roughly 1 to 2 degrees Celsius. The no policy graph is in the lower right-hand side, and that is a world that's much hotter than it is now. It's a world that's historically unprecedented. We haven't seen conditions like this except in rare intervals, even in the recent fossil record. So it's a completely different planet. The challenge that we face dealing with climate change is really illustrated nicely on the right, on the left, with these panels. This is what happens with essentially no policy all the way to imposition of really dramatic policy over the next 25 to 30 years. Look at this. There's essentially no difference between the different worlds. That's because all this change that's occurring now is climate change that was committed by historical climate emissions, the ones in the past. This is also the reason why this is such a tough problem politically. Essentially, what you're telling the public is that commit to potentially drastic change, or at least severe change. We would have to move to a much more sustainable energy production network. That actually might be fine, but in any case, change will, the upper left-hand figure is dramatic change, the lower left-hand figure is no change, and there's no benefit, no appreciable benefit in terms of temperature over a 20-year time span from now. This is one of the reasons why this is such a tough problem politically. And essentially you're asking people, you know, okay, make a choice, but the benefit's going to be realized far in the future. That's the dilemma that we face. But I think it's a dilemma that we have to face responsibly by first facing the facts and then asking how we want to deal with them. And a number of really great thinkers have thought about this problem hard. And I'd like to end with a quote from E.O. Wilson, a very famous scientist at Harvard who's studied ants his entire life, but has also now begun to address the issue of our impact on the natural world. And he said, "A very Faustian choice is upon us, whether to accept our corrosive and risky behavior as the unavoidable price of population and economic growth, or to take stock of ourselves and search for a new environmental ethic." And it's with that thought that I would like to leave you and turn the floor over to my colleagues who will now explore other aspects of the climate system, including climate impact at high latitude, and that's what we'll be hearing about next from Margaret Torn. Thank you very much.
Hi. Yeah, good evening. So we can get this to move. Let's see. Yeah. So they'll start that. What I want to do is shift gears now, move from model world up to the Arctic, and look at the effect that warming may have there. So this is Ivatuck, Alaska. It's on the north slope of the Brooks Range, and this photo was taken in August 2011. I went there with a team of scientists studying climate change, and we walked a transect here, putting a little pole in the ground, see how far we could go. We were looking to see the depth of permafrost thaw, and we could go about 50 centimeters or 20 inches everywhere that we went. And at that point, we couldn't go further, and that's because we hit frozen ground. And the ground here is frozen year-round, doesn't come above freezing any time of the year, and that's permafrost. And the permafrost can be a meter deep. It can go 100 or even 1,000 meters deep of this frozen ground that's been frozen mostly since the Pleistocene. In the summer, it thaws somewhat, as I was saying, and that's where the plant roots get their nutrients. But it's just a shallow skin, and the rest is frozen. And this map up here, it's a different kind of view. We're looking from the North Pole down onto the Earth, and you see here this purple shading, and that's showing the extent of permafrost, this permafrost ground or perennially frozen ground. It's very extensive. It goes all through the Arctic, and the northern part of the boreal forests are also underlain by permanently frozen ground. And what I want to talk to you about is just give you a brief look at what happens when this perennially frozen ground begins to thaw. I was visiting that site with a group of scientists, as I said, studying climate change, and I'm a biogeochemist, so I'm not studying the permafrost itself, but rather how ecosystems affect climate by releasing greenhouse gases or changing exchange of energy and water with the atmosphere. And the Arctic is indeed vast, but I want to say that for me, the biodiversity strikes you on a miniature scale. It's the moss and the lichen, and in the middle here, that's a blueberry shrub with its one blueberry. They are delicious, but you have to keep moving, which is probably what I'm doing in that photo. It's just getting another blueberry. Yeah. So as Bill pointed out, the Arctic is warming, and as his simulation showed, the darkest red is at the top of the plot. The Arctic is warming faster and will warm more than any other part of the Earth. And in fact, it's already warming. So what Bill showed as warming from 1950 to the present, that's about 1 degree Fahrenheit on a global average. But this map of Alaska shows that in Alaska, it's warmed about 2.9 degrees Fahrenheit over that same period, 3 times as much. And the projections are the same, much more warming there. But as it's already warming, permafrost is already thawing, and it's having local impacts like the foundation of houses slipping in because the ground isn't solid beneath them, or trees tipping over. It's called drunken trees. And it happens naturally as well, but it's happening more now. But what I wanted to talk about was not these local impacts, but the way in which permafrost thaw will feed back to global climate. And how is that? Well, one of the main reasons that in that frozen ground is frozen old buried carbon from many years ago. The organic matter could be a woolly mammoth, or it could be from a microbe decomposing plants. And there's deep, deep profiles. It's a little hard to see here, but what you're seeing is these dark areas here are organic matter going deep, deep, deep. This is about I think 50 meters high. It's cut for us, but this area goes on. This is from Siberia. The whiter areas are ice that are also frozen, so the ground is held up by excess ice. One thing that's interesting here is that if that ice melts, the ground actually subsides. There's nothing to hold it up, and you end up with very interesting shapes, and that's one reason that the trees fall over. But there's a lot of carbon in there because it's frozen, just like the food that's preserved in the back of the freezer. Here's a deep tropical soil, and it's as deeply weathered, but it has only 1/10 of the carbon. So it's really a lot of carbon locked up there. And if it were released to the atmosphere, it would more than double the amount of CO2 that's currently in the atmosphere. So that's a huge effect. So if you imagine, go back to your freezer for a minute, and if your freezer's like mine, there's a little bit of food there stuck in the back. I don't know what it is, but it's been there a while. If I were to unplug the freezer, just let it sit for a week, and I came back, it would not smell very good, and the food would have rotted. And the point is that when it gets a little warmer, then the microbes can become active and start decomposing that organic matter. And when they decompose organic matter, they form CO2. If they're doing that in a dry environment where there's oxygen, so the O and the CO2, if the decomposition is happening underwater, it's a little hard to see the little inundated area there, then you're going to get methane. There isn't enough oxygen to form CO2. And it's important that you get both of those greenhouse gases. One reason is because CO2 is per molecule, or even as a global warming potential, about 25 times more effective in warming than is CO2. So we care about the amount of greenhouse gases coming out of the ground, and also, is it methane because the ground is wet, or is it CO2 because it's dry? Now you're probably thinking, well, from what we heard from Bill, if there's more greenhouse gases, there's also more warming. So we can have warming that's causing more greenhouse gases, that's causing more warming, more permafrost thaw, more warming. That's a positive feedback loop. And it's called positive in the sense that it amplifies the perturbation, not because it's necessarily a good thing. And in this case, it's not a good thing. It means that it will keep going in a warming cycle. Now, one question you might ask is, well, was this effect already in the model we just heard about from Bill? And the models that Bill showed do have a land surface, but I'm afraid they don't have all these processes. So they don't simulate methane production, for example. They don't simulate real changes in plant distribution across the landscape. So what I'm talking about here is an additional effect, in addition to what Bill was talking about. So when permafrost thaws, not only do you get more greenhouse gases, but other things happen too. That decomposing organic matter mineralizes nitrogen that's more plant available. The growing season is longer, air temperature is longer. So those things promote plant growth. And plants take up CO2. So here I'm showing a grass, Eriophorum, going to, this is a birch tree. It's about this tall, but that's fall in the Arctic. It happens also in August. But the shrubs can grow higher, they can take up more carbon, so that's a cooling effect. At the same time, though, those shrubs cover snow a little bit. They're a little taller. They're darker than the snow. That means they absorb. Can you hear me now? Excellent. So they change the albedo. So plants can have cooling and warming effects. Therefore, it's a rather complicated picture. And our research questions are, so what controls the balance? Will microbial decomposition and release of greenhouse gases dominate, really increasing the greenhouse effect? Or will plants grow in such a way that they help cool? And it's a rather intricate set of connections between landscape hydrology, soil microbiology, the soils themselves, plants that determine that balance. So we're researching that in a large experiment that's being funded by Department of Energy. It's a large team. It'll go on for about 10 years. And we're trying to understand that intricate set of relationships and then put those processes into a model that can represent the complexity within Bill's larger global model so that we really get a more accurate prediction of climate change feedbacks. And these are just a few illustrative pictures. I'm saying that we are working up in Barrow, Alaska. That's the furthest north part of the United States. And then we're going to be moving in a transect south. And this middle picture is showing patterned ground. This is really fine-scale heterogeneity that's made by that ice, and I'll show you a better picture of that in the next slide. And the upper right is a graduate student, Melanie Hahn, and a colleague, Dave Billisbach, putting up instruments we'll put up in a tower that measures CO2 and methane flux over a large area. These are very fast response laser-based instruments. So one thing that's really neat about the Arctic but makes it very hard to predict change is that it forms these really interesting pattern grounds. Up in the upper left there is low-centered polygons, and it's excess ice that has pushed up and made these edges that hold the water in. And it's a little hard to see, but this picture here is showing a cutout of ice. There's some white ice there underneath the green grass. And if the ice melts, then you completely change the topography. And there is no model right now at the global scale that can represent anything like that. And what's showing here is kind of a negative image of that one. It's after you have thaw, the edges subside, there's no more ice, the water drains away, and this gives off a lot of CO2. It can give off so much CO2 that it actually contributes more to warming than that wetter area would, even though the wetter area is giving off methane. So what are we seeing? Just to show you two quick results from lab experiments. The one on the left is a microbial experiment. It's it found that when you thaw soil, you can immediately get more methane production. And it was a very deep genome sequence, a metagenome. It was looking at every microbial taxa in that soil, one of the deepest metagenomes ever conducted. And it showed that the metabolic potential is there to respond quickly and to decompose all the different kinds of organic matter in the soil. But also that little ring there, which obviously you cannot see what it is, but it's a genome for a novel methanogen, one that hadn't been known before. So there's also a lot of mysteries about exactly what's there and how it will respond to warming. On the right-hand side is a project from Lydia Smith, a graduate student, looking at warming the soil right at the permafrost active layer boundary. And with just a little bit of warming, we got CO2 that we could date with C14 and show that it was 2,500 years old. So just a little bit of warming would make that material, very old buried material, available to microbes. In the field, people are seeing the same thing. Katie Walter Anthony is pictured there on the left, and she was finding methane coming out of these lakes that was as old as if it had been perhaps from one of those woolly mammoths. This on the right is another field experiment from a postdoc, Caitlin Prees, and she's measuring the CO2 coming out of the ground at sites with deeper permafrost thaw, or this thawing happening. And from the C14 of that CO2 showing that the deeper the thaw, the older the organic matter. That means you're releasing carbon that was locked up. It wasn't participating in the carbon cycle, it's kind of there at the back of the freezer, and it's coming out. So the question that was posed to me in preparing the talk is what happens to Earth's climate when permafrost thaws? So we don't have a forecast yet. I'm showing you work that's just in progress. But we could look to some published estimates of permafrost release. So in the units that Bill was showing, 1 gigaton is 10 to the 15th grams of carbon per year as CO2. What 1% is methane, so very small amounts, a conservative estimate of the methane flux. And on the units that he showed, that's emissions of 4.6 gigatons. So I'll put this on the same plot he had. That red arrow then is how much additional warming or additional climate forcing coming from CO2. So it takes us from, for example, a scenario in which we had successfully mitigated, this is the happy Bill McKibben scenario, up to sort of the next level. If we don't mitigate for a while, it does the same thing. So it's really adding quite a lot to the warming. One other way to look at this is to put it on the scale of the amount of CO2 emitted by coal plants. So that amount of emissions from permafrost thaw, contributing CO2 and methane, is equivalent to the emissions from all the coal-fired power plants in the United States right now. And that's a daunting number, but there's also something else to consider. We could, if we want to, shut down the power plants. But it's much harder to control a positive feedback that is going on pan-Arctic. So it's one of those things that you want to prevent, as opposed to coming along behind. So I'm just going to end very quickly with some thanks, because we are working in the borough of Barrow, and I want to thank the people there who have been really helpful to our work and are great scientific partners. And now I want to turn it over to Michael Wehner, who's going to come talk about climate extremes. So what happens with all this increased warming? Thank you.
I'm going to talk about extreme weather and climate. And you might think, what's this guy talking about? Weather, climate, what's the difference there? I had the privilege as a young scientist to hear a banquet talk and meet, actually, the great scientist Ed Lawrence, who's the father of chaos theory. And the title of his talk was Climate is what you expect, weather is what you get. And I really like that definition, because that's what climate really is. It's not just the average of all the weather that we get, but the whole statistical description over a long period of time of the weather. Extreme weather is of interest to me because we live in the weather. We don't live in the climate. We live in what mathematicians would call the noise of the climate. And the impacts of extreme weather are where the rubber hits the road in this business. And, oh, here we are. Oh, geez, it's not supposed to do that either. There you go. So here's some examples of what I mean by this. I'm going to keep an eye on this, make sure it doesn't change on me again. Thank you. So heat waves. I mean, we had a heat wave today. I was really uncomfortable. I don't know about you. And in fact, records are being broken as we speak. Cold snaps, which are the opposite of a heat wave. A drought, which we've just experienced some very severe ones in the United States, but elsewhere in the world as well. Floods, which strangely, perverse as it might seem, in a future very warm world, both droughts and floods become more likely. That's a complicated thing. I'm not going to go into it, but it is sobering. And then extreme storms, which is of particular interest to myself. Hurricanes being probably the most violent storms that the planet can have. Atmospheric rivers, you might have heard of this phenomena. The weather forecasters call it the Pineapple Express. We had one in December. It's called the Pineapple Express because the storm comes right over Hawaii, and it can deliver copious amounts of rain and wind. Typically, it's kind of warm compared to other winter storms we get here in California. And an impact we had at the lab was during that event, there was a landslide and blocked off the road. And so now when I go on my bike ride, we got to go all the way around. It takes another 10 minutes. Extratropical cyclones also impact us here in California. Those are larger scale systems. And then I've got down here, sort of separated from all the rest, are tornadoes and hail, high wind, lightning. These are examples of extreme weather where the state of the art hasn't gotten there yet. We very much would like to be able to make some statements about how these things will change in the warmer world. And I'm optimistic that in the next few years we'll be able to, but we're not there yet. Oh, there we go. So a question you might have are some of these recent events that I just mentioned, are they a result of global warming? So this is a really good question, but it doesn't have an answer right now. And the reason it doesn't have an answer is that any extreme event that has happened so far could have happened prior to the human intervention in the climate system. So, the heat wave that we had last year in the central United States, the drought in Texas the year before, the Russian heat wave, these events all were possible. And so we can't really answer if this particular event happened because of climate change. Now, that's not to say that in the future there will be events that couldn't have happened in the pre-industrial age. And I actually believe that if you go, Bill talked about choices, and one of our choices, let's not do anything, the no policy choice. And you go 100 years from now, and it's very likely that there will be heat waves and probably floods in that world that could not have happened prior to the climate change that was caused by humans, and would have happened perhaps in the very distant past, maybe 100 million years ago, but not any time since humans roamed the planet. So a better question to ask than this first one, as much as we'd like to answer it, is how has the risk of an event changed? And so that's a question we can get our hands on. How has the risk of last year's drought changed? I mean, was it more likely? Probably was. Or a similar question, it's almost the same one, is how has global warming changed the magnitude of that heat wave? Or that flood, or whatever it is. So here's some numbers, and this is my only real technical plot, so I apologize for all the detail, but I think it's interesting. The European, it would be more interesting if it wouldn't do that. The European heat wave of 2003 caused 70,000 excess deaths, which is pretty sobering. That's been well written about. It happened in August. A lot of people were on vacation, and the people who died were elderly and weak or sick, one of those, if not all of those. And the risk of that event actually was at least doubled at the time it occurred by the influence of humans on the climate system. And similarly, the Russian heat wave in 2010, which had 50,000 excess deaths, so 50,000 people died during that period in that region, more than would have in a normal year, was 2 to 3 times more likely because of climate change. There are other impacts as well. A lot of the surrounding area around Moscow burned because peat bogs had been drained and they got all dry, and so being that hot they burned, which further compounded the fatalities because the air quality was so low. And Texas, which is more close to home, I have a range here somewhere between 1.5 and 4 times more likely. And in fact, this is the way I prefer to look at it, is not to say just one number, but rather try to put some uncertainties on that. And, but it's still 2 is definitely well within that range. We're working on last summer. This takes some time, and so we're not in if next summer is hot, I won't have an answer until the summer after, but we're working on this one. But one thing that is sobering is if you look 10 years from now, remember the European heat wave is 10 years ago, so 20 years after the event, that event now, instead of being twice as likely, is 35 times more likely. And by 2040, which is sort of the end of the period where whatever we do now doesn't matter, it's after that that our choices matter, it's basically going to happen almost all the time. And in fact, if I can do this here, this plot here shows the probability of such an event happening. And our median estimate is that it's about going to happen 9 summers out of 10. So the phrase that I use for this is today's rare event, because back in 2003, this thing had some chance, single-digit % chance of happening. So today's rare event becomes commonplace in the future. And in fact, it's not even that distant in the future. But not all events are equal, and you can see that for the Russian heat wave, it's only 5 or 8 times more likely, so it has a chance of maybe happening once every 5 to 10 years. And the U.S. drought, or the Texas drought, maybe 4 to 10 times more likely, so it might happen 2 out of 20% of the time. So what I'd like to leave you with is this movie that keeps on wanting to come up, which is my latest calculation that I've been doing at the machines here at NERSC, the National Energy Research Supercomputing Center. And it's a global model. It's about as high a fidelity as we can handle. We divide the planet up into grid boxes, 25 kilometers on the side, and then integrate it as far as we can. And what I'm showing here is the water vapor, and let's just go to it, and I hope it plays. Very good. And you can see weather happening. Now, this is a climate model. We're going to run it for many, many years. I'm only going to show you a couple of months. But it's making hurricanes. It's got these storms here, and it's got weather fronts. There's some atmospheric rivers that flow in the right time. What I've shown you here, then, is what the models that are much coarser. The grid boxes are 200 kilometers on the side. These are the class of models that were used in the IPCC 4th assessment report. The 5th assessment report that Bill and Max and I are working on are somewhat finer. And I don't know if we can go back. Maybe we can go back and watch it again. For those of you in the back, especially if you take your glasses off, when we get to the part where the 2 of them are going, they kind of look the same. And it's only really when you look at it closely and you see the details of the fine weather that they're different. Well, maybe it won't play. But that's a good thing that they're not that different on the large scales, because that gives us confidence that the projections that we make based on those models in the IPCC reports have some legitimacy. And I don't think it'll play. Well, anyway, I'm going to go on and introduce Jeff Chambers, who's going to tell you about trees. And thanks for your patience with the technical difficulties.
Hello, everyone. So, all right. Get this to work here. So every one of you emitted CO2 to the atmosphere today. Some more than others. And how much of that CO2 actually stayed in the atmosphere? How much? 50%. Only 50% stayed in the atmosphere. Where did the rest of it go? Okay, well, here's our emissions. Half of it stays in the atmosphere. Well, half of that remaining 6 goes into the oceans. And the other half, it seems, I mean, there's some uncertainty here. The other half is basically going into forests. And most of that other 25%, half of half, is going into tropical forests. So remember, only 50% of your CO2 pollution stays in the atmosphere, and 25% of your pollution is being mopped up by the Earth's forests. So that's Hurricane Katrina, and I was on faculty at Tulane University, and I went to sleep at around midnight, and I was reading the forecasts. And they said Katrina might strengthen overnight. So I woke up, and it was 4 a.m., and I kept thinking, strengthening overnight. So I had to get up, and went to the computer, and that's what I saw. And I thought, wow, that doesn't look good for New Orleans. So my wife, who had just recently moved to the States, in January, so she was there for 6 months. She's from Brazil, and they barely know the difference between tornadoes and hurricanes in Brazil. And she's not much of a morning person. So I took my laptop to her bedside, and I said, Joanna, we got to get out of here. She said, what time is it? I said, it's 4:30. She goes, oh, come on. We can wait a little bit. And I said, no, we can't wait. And I showed her that. And she was convinced that, yeah, we needed to hightail it. So we left, and we went to Hot Springs, Arkansas, because I thought that sounded like a good place to evacuate from a hurricane. Now, when I moved to New Orleans, I'm from California. I grew up in Santa Cruz. I also didn't know anything about hurricanes. So when I moved here, and I study forests and disturbance, mostly in the Amazon, mostly in the tropics, I'll show you that too, I thought, I want to set up some plots and start studying these processes, right? Well, this is what I got. So I set up my plots at the Pearl River. Now, the Pearl River defines the border between Louisiana and Mississippi. Bullseye. So 2 take-home messages so far. Remember, the Earth's, the oceans, the forests are mopping up 50% of your CO2 pollution. That's a nice ecosystem service. The second is that climate change is fascinating scientifically. It's really interesting. And in fact, sometimes it's hard for us not to get so excited about the science that we forget that some of this can be quite destructive. I mean, just think about the losses of lives and property from this storm. Michael just talked about all those heat-related deaths in Europe and in Russia. And we're just getting started. So over the next 10, 20, 50, 100 years, we're going to learn a lot about how this system functions, a lot. But at what cost? So what this is it's a method called spectral mixture analysis. This is a Landsat scene. That's an airport. This is Bay St. Louis. This is ground zero for Hurricane Katrina impact. Anything that's green on here means thriving vegetation, and anything that's red is dead. So you'll see before Katrina, after Katrina. Before Katrina, these are false color, remember. Green, live, red, dead. Before Katrina, after Katrina. This is the Pearl River here. Before Katrina, after Katrina. And the area as I was setting up this research was up in here. And you'll see that some of this is red and some of this is green. So if you do a delta, if you subtract 2005 from 2004, basically subtract this image from that image, you'll get the delta. So that's what here, this is the delta image. We use this image to send out a crew to field sample. And it's really tough working in these post-disturbance environments. We had to buy those hedge trimmers and essentially carve tunnels through blackberry briars to get to some of these locations. And we use that to calibrate our satellite data to estimate how many trees were killed by Hurricane Katrina. That had never really been done before, and we came up with a number, 320 million. And that's the equivalent of the net gain by all US forest in a single year, the net gains, right? Okay, so let's move on to the Amazon. So I've been working here, this is Manaus, the city of about 3 million people in the middle of the Amazon. I've been working up in these forests for about 20 years now. In 2005, the same year as Hurricane Katrina, apparently driven by the elevated sea surface temperatures in the North Atlantic, this massive storm, I don't know if you can see quite South America, but I'll outline it for you. It's just about like that. That's a massive storm blasting across. So let's do it again. Oh, this is a blowdown. This is what happens when a squall line produces microbursts and wind speeds in this burst swath can exceed 300 kilometers per hour. That's about 600 football fields worth of forest that's been blasted down by a downburst. This is one of our field areas. This is a Landsat scene. Here's a road coming in. It's about 10 kilometers across. This is 2004, and this is 2005. So you can see all these areas. So again, send out the field crew, sample these gradients, and calculate how many trees were dropped in the Amazon in that event, and we estimated 500 million. And this is Juliano, a Brazilian graduate student who was doing that tough field work to link to the satellite data. So now we can start to build these mortality maps. And something else that's important is putting these types of relationships into the models. So it's not just wind either. It's also drought. So in 2005, there was a drought 100 years. It was at a in Manaus. Is the mic problem here? Oh, there we are. Okay. Here's the drought from 2005. And here, 5 years later, there was an even more severe drought than the 100-year drought that occurred in 2005. And this event caused widespread tree. I'm losing my mic again there. Drought is another concern, and it's expected to also increase in frequency with a warming climate. Outbreaks. So here you see North America. These areas in red here are regions that where trees were attacked by pine beetle, and here showing widespread mortality caused by this beetle species. Fires. So as the Earth climate, the fuel for forest fire, down trees, coarse woody debris. All right.
It's okay.
Are you going to turn that off? All right, let's try this. So not only is the fuel for these fires going to be drier and more combustible, but there's a lengthening of the season where, for example, there's no snowpack. So we expect fires to increase with a warming climate. So to summarize, storms, drought, fire, pests and pathogens. Looks like kind of like Armageddon or something, right? And you think, it's all bad news. But you know, something else interesting that we're finding is that, you know what, the forests are keeping up. So we started this off by mentioning that 50% of your CO2 pollution is being taken up by the biosphere. Half of that goes to the ocean, half of that goes to the land, potentially to the forests. The soils are more difficult to understand with respect to the sink. So this is a big carbon sink. Margaret pointed out that in particular high latitude soils can be a big carbon source as the climate warms. But what's remarkable is that despite the fact that our CO2 emissions are increasing year after year after year, on average, this airborne fraction has remained at about 50%. So my job is essentially to understand where this carbon sink is going in the future. It still cleans up a significant fraction of our CO2 pollution, but how long will that last? And what will be the potential carbon cycle feedbacks with respect to tree mortality as the climate warms? So originally, I was going to end on this talk. This is a student of mine took this picture in the Upper Rio Negro, one of the least populated places on planet Earth, less population density here than the Sahara Desert. And then on Friday at 7:45 a.m., just 3 days ago, 7:45 a.m., I was getting ready to take my daughter to preschool. And my wife was 8.5 months pregnant. And at 7 a.m., she said, I'm starting to feel some contractions. So she was on the phone to her doctor, 7:45 a.m. So I dropped Naomi off, and I was coming back, and I get a frantic call from Joanna, and she says, the baby's coming out, I've called 911. That's 8 a.m. I'm in the house by 8:01, and sure enough, Nathan's halfway out. It's just me and Joanna. Fireman arrives at 8:05, okay? And then at 8:10, here he is, Nathan was born. So I'm hoping these guys are going to live to be 90 years old. That's going to be around the year 2100. What is this planet going to look like in 2100? So we're going to learn a lot about how this Earth system functions, but what's the cost? So thank you, and we'll leave it there. Thanks.
All right. Happy Earth Day, everyone. You know what? You're at a really nerdy event if they bring out a German economist to close the show. There you go. I worked on that one. Where's the clicker? Did you take the clicker with your baby picture? There you go. All right. So what I want to talk about a little bit is, what does this all mean, and what are we going to do about it? And if we're going to do something about it, how much of this is realistically going to happen? So, fast forward 10 minutes, you're going to be really depressed. So let's look at where we are today. We started thinking about this problem a while back. So 1992, I believe, was the Rio Earth Summit. We just celebrated its 20th anniversary last year. In 1997, we signed the Kyoto Protocol, first global agreement to regulate greenhouse gas emissions. It was amazing that some countries worked together to achieve this. We are now, this year, at the 18th meeting of the parties, this is the 18th time we've met to negotiate a binding agreement and a successor agreement to the Kyoto Accord. We're not even close. You read the newspapers, you know where we are, I don't need to tell you, but we're a long ways away from something meaningful that includes the major emitters of greenhouse gas emissions in this world. The last line behind me says something depressing, like in 2011, emissions were 56. Yeah, that's right, 56% higher than when we had data for the Rio meeting. So this is depressing. CO2, from an economist perspective, is a stock pollutant. What you pump up there essentially stays up there for as long as I think most humans will live. I know there are some issues the scientists have with that way of thinking, but most scientists have lots of issues with the way we economists think, rightfully so. So this is what I like to call carbon mountain. Carbon mountain is sort of an unorthodox way of graphing emissions because time is going in two directions. Did I mention I'm an economist? So from the left, we start in about 1850, we go through 2010. This PRC stands for the People's Republic of China. This is Chinese CO2 emissions from fossil fuel combustion until 2010. You see that that peak is slightly higher than what happened in the US, time going backwards, starting in 1850, here going to 2010. The PRC is now emitting more CO2 from coal alone than the US is from all fuels combined. And if you look at the derivative of this thing, there's some saying, well, maybe this year emissions will only grow by 8% instead of 10%. It's growing rapidly. So the thing we, of course, worry about is not the level of this, but it's the area under these two curves right here. That's the total amount of carbon we've emitted into the atmosphere since the beginning of the Industrial Revolution from these two countries. What do these two countries have in common?
Biggest economies on Earth.
That, and neither of them are subject to any meaningful climate regulation. This, of course, excludes California as of January 1st of this year. Thank you. A lot of people worked really hard on that piece of regulation, so I think a little bit of applause is in order there. But when we think about impacts of climate change, the previous speakers did, I think, a just absolutely fantastic job of showing how scientists think about this problem. And economists, we learn a lot from this way of thinking, but there's two additional things that we bring to the table here, and we, all jointly under the IPCC collection of scientists try and explain that it's not just the direct impacts. It's not just that heat drops yields. It's not just that snowpacks are melting or coral reefs are bleaching. There are other costs here. The two major costs that we also have to think about are the costs of mitigation. That means the cost of actually reducing CO2 emissions from, let's say, power plants or whatever it is you're using to cool your car, which is a really powerful greenhouse gas as well. And then, of course, the costs of adaptation. Some of these costs of adaptation are things like we may have to build higher seawalls outside of SFO to prepare for 100-year flood events that are now higher than the ones we previously thought. Others are ones where you voluntarily now install an air conditioner in your home in San Francisco, which you wouldn't have thought of 50 years ago because summers were never really that hot. So what do economists do in their free time? Here we go. Actually, this comes out of Lawrence Berkeley Labs. An interdisciplinary group up there looked at some of these impacts of climate change. And I really like the interdisciplinary angle of this type of research, where what they did here is they laid over the map of California's electricity grid, that's what looks like veins in California back there, the fire risk map, meaning how likely you are to experience a wildfire in any given year, and looked at how likely are transmission lines going to be affected by wildfires. Then they took one of these fancy climate models, actually a bunch of these fancy climate models, and looked at how the probability of these transmission lines being affected by wildfires under climate change is going to change by end of century. Lesson is red's bad, green's not so bad. So what you're seeing up here, these nice transmission lines that are bringing nice clean hydropower from the north are likely going to be more affected by wildfires under climate change than not. So this is just an example of a lot of little studies that we're all trying to piece together in a more universal picture of impacts. This is some of my own work here to just outline how important and how significant temperature, the role of temperature is in electricity consumption. So this is the California Independent Systems Operator load by the hour. And what I've done here is I've essentially fit a nonlinear function of load to temperature. It's not that surprising that when it's really hot outside, electricity load goes through the roof. Why is this? Have you ever been to El Centro? It's hot. All right? Sorry, I should not breathe so heavily into the microphone. So what do? You turn on your air conditioner. Air conditioners, unless you have a really nice heat pump, you're going to use electricity to work it. Well, in California, this is an issue. But let's look next door. This is China. All right? This is some data I've collected recently from official statistics right here. What you're seeing, if I may walk up here without falling off the stage right here, these are China's 30 provincial entities. The little black bars right here were air conditioners per household in 1995. The light gray bars are air conditioners per household in urban households in 2009. That's a 15-year period, and you can see a slight change. Guangdong, Shanghai went from about 0.4 air conditioners per household to roughly 2. All right? What this means is going forward, as it gets hotter outside, areas that previously didn't have air conditioners will get air conditioners, and this is all amplified by the role, of course, of growing incomes. As we get richer, as the prices of these things decrease, and as it gets hotter, we will use more of these gadgets. So trying to understand the magnitude of these effects is really important, and that's what a lot of social scientists spend a lot of time doing. So I was actually invited not to talk about this stuff, but to talk about regulation. But that's the beauty of standing on stage. You get to talk about what you want to. So what economists, when we think about regulation, we think about regulation in 3 ways. Standards, taxes, and cap and trade. That's how most pollutants are regulated. Standards are the things we're used to. This is how I regulate my 4-year-old kid. The standard is 10 minutes of iPad a day, and that's it. It's strictly enforced, right? You can think of a pollution standard the same way. You may emit this much NOx, CO2, whatever it is. It's strictly enforced. If you go beyond that, you pay a fine. This is how we've thought about regulation mostly. You can also think of technology standards where you tell people what type of technology they have to install in their factory, like the SCR scrubbers we put on power plants to get out NOx, for example. And we also have so-called input standards where we tell people what they get to put into their power plants, low sulfur coal versus high sulfur coal. Economists hate standards, generally speaking. They're very inefficient. They're very high-cost ways of reaching a certain goal of emissions reduction. And I'm sure we can argue about this over Q&A later, but I'll just let that stand in the room for now. Taxes we really like, and cap and trade we also really like. Why do we like taxes? Well, let me tell you all about it. The other reason why economists aren't so much fun to listen to, we don't have maps and animations. We have text on our slides. Not so good. So essentially, why do economists like taxes? Remember one phrase, tax bads, not goods, right? What we want to do is we want you to pay the full cost of all of your activities. So if you drive down your car and you don't pay the full cost of using the atmosphere as your personal carbon waste dump, I think the government should charge you that difference that you're currently freely using. We call that an externality tax, or a Pigouvian tax, if you wish to call it. It's efficient. It makes the world better off. You can use the revenue from this to offset bad taxes. Income taxes are actually not such a great idea, right? We don't want to punish people for working more. I'm not making an equity argument here, but all right. All right. We can get to, welcome to Berkeley. We can get to that in a second. But taxes actually set nice incentives for people to develop new technologies, but in practice, they're not very practical. Why? Firms hate them because they have to pay them, and politicians hate them because the firms have to pay them. So the issue here, they're politically really hard to push through. Cap and trade, what we currently have in California, are slightly different in the sense that the regulator sets the total amount of emissions we'll allow, and then issues rights to pollute. Where's the boo? It's coming. There you go. Issues rights to pollute, and then these are traded. In fact, if you actually came to my economics class, I would teach you that these two, under certain settings, are roughly equivalent, right? They're efficient, and they get us to the right pollution level. So what's the problem? We don't just have to get a single country or a single state to do something. This is a global issue where we have to get everybody to do something. So we're currently trying to get 200 plus nations to reduce their greenhouse gas emissions. This is a tough thing to do, right? We're trying to negotiate this global accord. It hasn't worked, no matter how optimistic a spin you put on it. The European efforts are slowly, political support is slowly coming down, if you've read the news this week. And there's just no significant progress on the horizon in this particular framework. I know the UNFCCC, which is the organization running this show, is arguing that this is a really sort of positive thing, and there's lots of opportunities to go forward here. But the track record has shown, in my eyes, that maybe we're taking a little bit too long. All right, so here's what I think I should do, what I think we should do. I know what I should do. So what I think is, instead of trying to get 200 countries to hold hands, let's try and get 20 countries to hold hands. By the 20 countries, I mean the G20, the biggest economies in the world, and have them to agree to charge a significant carbon tax. Let's start at 20 bucks a ton. Not that bad. Why would anybody want to do this? If you are China and you're having trouble collecting income taxes, it's much easier to collect a carbon tax than it is to go to every household and collect an income or a payroll tax. It's efficient. You can enforce it at the border. If people are trying to sell you stuff into your country, you just enforce the tax at the border if they don't have a carbon tax at home. Same thing goes for the US. All imports that come from countries that do not have a carbon tax get that enforced at the border. There are some issues here, right? We can discuss those later. But the point here is, as a starting point, this covers the majority of emissions. It moves us in the right direction in an efficiency argument. And it can be negotiated much, much more easily. Still incredibly difficult, but it's easier to get 20 people to agree than it is to get 200 to agree. So this is all I've got for now. I have no cute baby pictures, unfortunately. I'm impressed that you showed up today. This is all I have to say. So thank you so much, and we'll talk.
Okay, we're going to begin the Q&A session. So folks, it's hard for me to see. We have, again, the mics are on this side, in the balcony, and located here as well as here. So while people are lining up for questions, we can start. You got one there, John? Okay, let's start on this side.
Early in the presentation, you showed some models on the screen. One was a green line that was very optimistic. And I heard a name, Bill McKibben, referenced. And I was interested in that very optimistic model, what actions were being proposed.
Let's see, is my mic on?
Should still be on.
Yeah, it is on, good. Well, I very much respect Bill McKibben and his work. That model actually required us to create a technology that we don't have that removes carbon dioxide from the Earth's atmosphere. So let me just repeat that. We have to remove carbon dioxide from the Earth's atmosphere. It assumes negative emissions by about the year 2050. Currently, we have no such great sort of rolades for carbon dioxide lying around. So that scenario is viewed as, we're not, by the way, in IPCC, we're not allowed to make sarcastic remarks about which scenario is more likely than another. That one, I think, would be characterized as mildly optimistic.
Did that answer your question? Did that answer your question? Yeah. Okay, let's take one over here.
I've been in the energy business, energy efficiency business for about 20 years, and it seems that in that time, the worst case scenario of 20 years has actually been surpassed by the actual scenario. Very alarming. What is going on with ocean acidification? Nobody spoke to this, and it seems that about 3 years ago, it came onto this, the large radar screen, and it is the scariest feature of all, as I understand it. Can somebody speak to ocean acidification in this process?
We're drawing straws here.
It will not be me.
Yes.
Yeah.
Jeff, I think you're the sacrificial victim.
Okay, so I've never worked in an ocean outside of maybe some deep sea fishing. But I've taught a bit on this in classes. I taught a global change biology class. And the interesting thing about that problem is it's quite different than a lot of the other problems related to CO2. And it's related to the fact that CO2 dissolves in water to produce carbonic acid. And there's a reaction sequence, right? So as you increase the rate at which CO2 moves into the ocean, it acidifies because carbonic acid is an acid. And it varies a lot, but organisms that produce calcium carbonate shells, be it diatoms or shellfish or a host of other marine organisms, there's frequently a very narrow range at which that precipitation of calcium carbonate is optimal. So there's a direct effect there. The other problem is temperature itself. So as temperature rises, for example, corals will expel their zooanthellae. Those are the algae symbiont that give corals color. And that's a photosynthetic organism that provides actually additional carbon to the organism. The coral polyps can actually consume other smaller organisms and also get carbon. But there's a range at which a lot of corals will literally expel this algal symbiont. It's really not well understood. That causes coral bleaching and frequently the death of coral reefs. So there's very complex processes in oceans related to the direct effects of CO2, calcium carbonate, and then just the temperature effects.
I will add, to any of you who do have questions, that we don't have the exact expert up here. You can always use our social media channels to leave questions there, and we will see that you get some answers. Person up on the balcony.
I have a question for Professor Aufhammer. I would like to hear more about the relationship between sort of the air conditioners in China example with people's purchasing power getting so escalated in the last 100 years. And I guess I would like to understand better how it is that the things we buy are so cheap when, in fact, they really are unrealistically cheap, it seems.
That's an excellent question, right? So, I mean, essentially what we spent whole semester-long sequences in international trade classes, but essentially what happens is countries specialize in the production of things that they have a comparative advantage in. So if you have things that require a lot of labor, and you have lots of low-cost labor, you specialize in producing those things. Transport is relatively cheap for most of these devices. So if you look at the ability to buy a window air conditioner today as a fraction of your income relative to what that would have been 25, 30 years ago, it is astonishing. Getting data on this is actually quite difficult, but it is quite astonishing. I think the bigger issue here is one where that air conditioner that you're purchasing, once you operate it, you're feeding it electricity. You're not paying the full opportunity cost of the electricity you feed. Even though we all complain how expensive electricity is and energy is, we're currently not paying the full opportunity cost of the resources used up to produce this. Also, what's inside the air conditioners are liquids that are really powerful greenhouse gases. We currently aren't paying the full opportunity cost. What happens when ultimately that air conditioner releases that full amount of greenhouse gases here? So from my perspective, the thing is artificially cheap because you're not paying the full opportunity cost of the resources. It's artificially cheap to operate. But there's a larger argument here as to why are all the things we're buying today so incredibly cheap. And that's, I think, a discussion that takes much more time than what we could do here. But a lot of that has to do with specialization and production of goods to places that are relatively inexpensive and frankly have much more lax environmental regulations. I mean, if you look at a lot of the local pollution that happens in the production of batteries and name it in a lot of these places, it's shocking. You would not get away with that here, which is partially why that production moves to those other places. So I'm sorry I sort of went around your question a little bit, but hopefully that gave you a flavor of my thinking.
Thank you for your question. Let's take another one from the balcony.
Yes, in Bill's slide, it showed at the end of the century, under no policy, about 4 degrees Celsius warming at the end of the century, and that was optimistic, I guess, because it didn't include permafrost. But taking that, climate scientist Kevin Anderson of the Tyndall Centre in the UK said about plus 4C. He said that that is not compatible with an organized global community, is beyond adaptation, devastating to the majority of ecosystems, and may not be stable, will lead to higher temperature. My question for everyone is, do you agree?
Well, let me start with part of the answer to your question, which is we need to look at this. I mean, a lot of this evening has been focused around the effects of climate change. We've sort of primarily been talking about people and then land surface and trees, but we began to touch on the topic of the impact on ecosystems with the question with regards to corals. People are very adaptable, right? We know what's coming. Unfortunately, the ecosystems around us don't. And the thing that I think that we need to keep, that needs to be a much more present value for everyone in this conversation is that, surprise, surprise, we actually do rely on the natural world around us, and we're putting that natural world through a great deal of stress. So ecosystems in parts of the world need to be moving twice as fast toward the poles than they actually are moving in order to survive. So one of the reasons why we sort of take these targets, and that's a very blunt instrument for describing the impact. That impact includes the impact not only on people but on ecosystems. And I think I just wanted to bring living organisms, plants, animals into the picture here because unless we are cognizant, at the end of the day, that this is not just a question of air conditioning our way out of this problem, that we also rely on having living forests and animals around us. And that's where some of these targets come from. And then to back up to the human impact side, the IPCC process has graded, essentially sort of translated different temperature targets into impacts on society. And they have a sliding scale. Once we get to 2 degrees Celsius, then you're starting to see significant impacts on tens of millions to hundreds of millions of people. So the 4 degrees Celsius is actually two times the target that, for example, Europe has been considering for some period of time. It's going to be a dramatically different world, and one in which ecosystems are under stress, and likely sea level will probably be 1 meter higher than it is now. So, yeah, it's going to be a very different world, and it'll continue to get even more different as we go into the future. 4 degrees Celsius is not the end of the story. I mean, I think the other thing I want to communicate, sorry for this run-on answer, is, but, I'm a physicist, and I guess I've seized this microphone here. The climate change doesn't stop after a century. We've been talking about year 2100. We've signed up for climate change for the next 3 millennia. Okay, think about that. 3,000 years ago. Why, that was back, at the time when the Greeks were just beginning to form their civilization. That's how long we're committed to climate change going into the future. So 4 degrees Celsius is not where we stop. We keep going.
Thank you for the question. Let's start over here.
A while ago, the science program called NOVA had a program about the effects of airplane exhaust on climate, and what that program basically said was that the clouds generated from the airplanes were actually kind of a shield which prevented the heating up of the ground temperatures. And during the 9/11, when they didn't have the airplanes, the temperatures went up dramatically. So I'm wondering if these climate models calculate the temperatures based on having jet fuel or jet clouds in the sky, or if their calculations are based on no jets.
I'll take that question. Yeah, that effect turns out to have been exaggerated in that study. We've looked at the effects of jet airplanes. This is actually a topic that's sensitive to me, given my status with United Airlines. But it turns out that the climatic effects of airplanes it's a balanced effect. You reflect sunlight during the day from the contrails. At night, those same contrails act to trap heat. There have been some coordinated efforts within Europe to switch to more, to eliminate night flights because those act to warm the climate. But the estimates for the effect of contrails are in the noise compared to the CO2 emitted by the planes. So those clouds are really having sort of a minor effect. CO2 at the end of the day and at the end of this century is going to be the dominant greenhouse effect, climate change agent, not contrails. We haven't included them because, yeah, that effect is like, it's literally a round-off error in the climate models compared to the other forcings from, say, methane.
Could I add something more?
Absolutely.
My mic is working, which I don't think
Yeah.
it is.
I think it should be working.
Oh, is it working? Okay. I agree completely with what Bill has to say, but the idea of airplanes affecting the climate brings up another thing that we haven't really talked about, and that's geoengineering. There has been a proposal that one could deliberately add something called, add sulfur to airplane fuel and create a form of pollution called sulfate aerosols. These aerosols are very tiny particles, and sulfate aerosols tend to be white, and so they would reflect incoming energy from the sun back out to space. And so you can, in fact, we have to account for this in the current climate to get the answers right, because it does have a cooling effect. And it probably would work to some extent, that you could cool the planet by dimming the amount of sunlight that reaches the surface. But there are all sorts of other ramifications of such an action to the hydrological cycle. You may make drought more likely in certain places and flooding more likely in others. And so the idea is very controversial and not without legal ramifications.
I do want to just add on to that point about geoengineering, which is that it's another one of these long commitment things, right? So you're signing yourself up for doing this. If you go the geoengineering route, so you think, I'm not going to actually fix the source of the problem, which is CO2, I'm going to put a Band-Aid on it, you're signing yourself up for applying that Band-Aid for thousands of years. And it doesn't, the one that Michael just mentioned doesn't do a darn for ocean acidification. So we've run experiments now where we turn this process loose, cool the climate, and then somebody has the budget cuts happen. Oh, woe is me, we can't fly these planes the same way we did. We turn it off. Climate change, the climate change that you've held off, kind of like keeping your fingers in the dike, comes roaring back, and it comes roaring back to the same level you would have been at in 5 years. So it's a no holds barred strategy. You go this route, you're committing yourself to 3,000 years worth of creating artificial volcanoes. So something to think about.
Thanks for the question. Next question over here.
Yes. A quick question and a general one. The quick question is there someone in your program working on the climate change effects in the Bay Area specifically?
Dead silence.
Yeah.
No, there was...
yeah. Max?
So there was a report sponsored by the CEC, and that also brought in the Bay Area ABAG, I forget what they stand for, the Bay Area Council of, yeah, there we go, thank you, that actually looked at climate change impacts in the Bay Area. It was a subset of the peer CEC scenarios process. So if you'd like to know more about that, I'd be happy to link you up with those people.
The question was, when you say impacts for 3,000 years, I agree that's starting to get the right time frame, but I don't know that there are mechanisms that deacidify the ocean and de-desertify the land and restore the polar ice caps 3,000 years from now. So isn't it really an untold number of thousands of years out that we're looking at?
Right. Well, the 3,000 years is the sort of the beginning of the ocean. That's the ocean overturning circulation time. The ocean stores 50 times as much carbon as the atmosphere. So you need, as the ocean basically begins to come into equilibrium with the increased CO2, it will draw it down. But if you actually look at the long-range view, you have to wait for geologic processes to set in to actually begin to store even more of that carbon. So getting the climate system back, and it's an excellent question, yeah, it's not 3,000 years, that's the down payment. It's more like a 20 to 30,000 year proposition. It's the interval between ice ages.
Next question from the balcony, please.
I have a two-part question, actually. First part, somebody mentioned the scariest aspect of climate change so far. To me, the scariest aspect I know of is the clathrate gun hypothesis involving melting methane in the Arctic Sea. And last year was pretty scary as well, the extent of global ice melting in the Arctic. I think we all know that it was the furthest extent of ice melt so far. There's a possibility within the next 5 years we're going to see open seas in the Arctic at some point. I don't know if this is widely accepted. That's my understanding. But I've heard that I actually saw sort of a specific study of the extent of methane emissions in the Arctic in recent years, and it seems to be pretty much just upward slope, exponentially rising methane emissions. The second part that I'd like to address is actually a lot more hopeful. What I've heard is that the most effective step that you can take against climate change is to not make babies and to limit population growth. Really, economically.
Oh, now that's
a low blow. This is not a joke. This is true. If you look at the economics, the most effective step you can use is to use a condom. So, yeah, it's true. And I would like to ask a third part of Herr Aufhammer about the possibility
we're going to limit you to two. Okay, we have lots of people
just to mention the possibility of a post-carbon, post-capitalist world and whether that's accepted at all by mainstream academic economists. I don't know if that's seriously accepted at this point. But I know that's going to take forever.
We will comment on your comments since I didn't really hear an exact question. But
yeah, okay. Well, I'd really like to know whether is there a serious threat presented at this point regarding what I've heard called the clathrate gun hypothesis, or that the melting clathrates.
Okay. We can answer that one.
Yeah. And the second part, is it true that the most effective?
Yes, we're going to answer one. We have lots of people waiting, sir. So we'll answer that very specific question.
Yes, we are investigating that issue. As Margaret pointed out, we are working hard on including methane as part of the models. We're actually using codes that are used by industry, the same codes that were used, for example, to look at the effects of the BP oil spill in the Gulf. So we know that we've calibrated them against real live clathrate releases in the basin. At the moment, I think it would be fair to sum up that by saying that it is a positive feedback, so it will amplify climate change. Is it a major threat in the next few decades? We don't think so, but the jury is still definitely out on this. We are looking very hard into it. But at this point, I would have to agree with Gavin Schmidt at NASA, who says essentially the methane is the icing on the cake. The primary driver here is man-made CO2. But this is science that's still under active investigation, and please stay tuned. I think in the next IPCC report, you'll see a lot more work on this. Thank you.
All right, next question up here.
Okay, so my question is, at the beginning of the presentation, you showed a number of graphs with different scenarios. What? Sorry. At the beginning of the presentation, you showed a number of graphs with different scenarios based on policy, and how much emissions per year there would be, and what that would influence the temperature. And you said I believe you said that didn't include everything you talked about today. So it didn't include. Margaret sort of noted briefly like how permafrost melting would influence it, but it doesn't include, say, tree death from drought or fires or pests or hurricanes or whatnot. So if you were to take into effect all of those things that we talked about today, and maybe some other things that would counter it, like what would the new scenarios look like?
Yeah, please. Yeah, I think your mic is on.
Yeah. Is my mic on? Okay, thanks. Yeah. I want to answer that in two ways. So one is that I did show sort of a red arrow going up indicating how big it would be. And in that case, ecosystems are emitting greenhouse gases, and they act just like anthropogenic greenhouse gases. So they're well mixed, and they sort of move us along that line from one scenario to another in a sense. in that way. And you could see sort of the relative magnitude. And something that was really important there is that the difference between those scenarios was actually very large and represents the difference in what we decide to do as humans. And that uncertainty is still the largest one, I think. So even though I'm studying the ecosystem feedbacks, and I really think they have the capacity to move us to a much warmer world, and it looks like most ecosystem feedbacks are positive. The paleo record shows us that ecosystems tend to form positive feedbacks to warming and amplify it. Still, I think that biggest uncertainty is going to be on the policy side, and they really just tell us that it's even more important to drive emissions down from what we can control. So, but I think it's sort of bounded in a way in what Bill was showing, at least from one, unless you're up at that upper scenario, and then it is off the charts. Yeah. So it could be something like 20%, sort of the estimate, you might say 20% increase. Is it not an unreasonable number for that? And then, yeah.
Was there a follow-up? When did we think it was going to happen? Was that your follow-up?
No, my follow-up, no. I was just wondering, if you include like permafrost as well as everything else, it's 20%?
That's a very rough number for this century, but things will keep changing. Yeah.
Thank you. Next question over here, please.
I understand, I believe it was an NPR show, alternative radio or something, I don't remember, but the point was that the temperature had gone up 1 degree centigrade, and that Kyoto only had one number in it, and that was that it would allow only 1 more degree centigrade. And I don't know if those are true facts, true or not. But the point was made that the fossil industries owned 5 times as much carbon as would be necessary to move it up to 1 more degree centigrade. And I'd like to ask the economist and back up with the others, if my science is right, that is it feasible that we could, whatever method we use, cap and trade or whatever, somehow convince these people that owned 5 times enough carbon to completely destroy, from what this reporter said, the Earth, from not doing that. And I'd like to, I have a second part, and that is very short.
Wait, could we just, we're going to answer that one question.
That is very short, and that is fracking. I want to just say fracking. Okay. Anyway, that's my main question.
Answer one piece of that. I want to expand on something that Max said about California. So California has found the will to really make a difference and take a different path, and I think it's worth taking just a moment to recognize that here and to see how we can build on that. California has a binding legislation to reduce our greenhouse gas emissions to 1990 levels by 2020, and there's an executive order, that's not binding yet, from Schwarzenegger to reduce greenhouse gas emissions by 80% of that 1990 level by 2050. And there have been now a couple studies showing that it is technologically possible to really transform our energy system, the whole infrastructure to do that that is possible if we continue to invest in energy efficiency and better energy technologies. So that possibility exists in California, and our existing legislation is taking us in that right direction. And it's something that we can build on.
Max, did you have something to add to that?
Yeah.
Always. The only meaningful global climate regulation, or the only meaningful climate regulation there will ever be, is one that keeps a significant amount of carbon, the majority of carbon in the ground, right? Everything else is essentially meaningless. So the question is, how do we do that, right? Coal, for the countries that need energy the most, is incredibly cheap, and the entire infrastructure, energy infrastructure and transportation infrastructure is set up around that fuel, and this is mostly India and China for now. We in California have done a good thing, I agree with Margaret, but we are one of the richest places in the world with one of the most active environmental movements in the world, with a tiny, tiny part of global CO2 emissions. So what we need to do is somehow figure something out that gets the rest of the world on board. And unfortunately, things in Europe are looking worse. Political support is dropping. We don't talk about that pipeline that is going to potentially put a whole bunch of unnecessary carbon into the atmosphere. But the point here is it's political will that globally keeps these fossil fuels in the ground. And if we can figure that problem out, then we've done it. But that's a tough one.
So, and Max, it's true that the U.S. is exporting coal to European countries, correct?
We're exporting coal to China, some of it. So, I mean, it's at this point, it's the flow of coal across countries is, an interesting thing to study. But it doesn't matter where you burn it. Whether you burn it here or there, it's a global climate system, and the effects will be felt everywhere.
Okay, next question, please.
I wanted to ask about the possibility of the Arctic Ocean becoming ice-free and sort of the timing, and do your models that you were talking about here include that very strong feedback, positive feedback effect in them, as I suppose they do. And I also wanted to ask, economically, are there countries or corporations that are already trying to get in to exploit the possibility of open passage in the Arctic Ocean?
So let me start with the first question. Yes, so the ice cover in the Arctic is declining at the rate of about 15% per decade. So you do the math. It doesn't take long to reach an ice-free condition by the middle or latter part of the century. Our models do project, depending on which scenario you look at, dramatic decreases in ice cover. They actually have not made it, the decreases are not as fast as observed in nature. So we're trying to understand why. In most cases, we're seeing a more gradual decrease, but we do forecast a largely ice-free Arctic by the end of the century. The reason why this is a feedback is that you're swapping a very bright surface that reflects sunlight, so it cools the climate, for a very dark ocean surface that's like pavement. It just soaks up sunlight, and that heats the planet, so it's a positive feedback. And I'll turn the economic side of this over to someone who actually knows economics. So Max, my understanding is that there are, yes, the countries around the Arctic are chomping at the bit.
So, I mean, people, if there's a buck to be made, somebody's trying to figure out how to make it. This is the way the system is set up. Yes, people are looking at ways to see of getting across that way instead of sailing, 5 times the distance and paying lots of money to get through tiny, tiny little passages to not having to go 7 times the distance. People are thinking about this and looking at this as a profit-making opportunity. People are seeking the resources under, wherever things are melting at this point too. So there's another level of economic competition going on. Yeah, people are maximizing profits.
So, somebody mentioned that population control might be a really important part of the solution, and I've got to say something about that. So we have a lot of good examples of developed nations that have essentially already solved their population problem. And the bottom line, and Max pointed this out too, is that if we send a strong pricing signal on carbon, make it $100 a ton. It's solved. The people that are out to make a buck, which is essentially most of us, we will solve the problem in a very short period of time. But how long will it take us to get to that pricing signal? How long will it take? If it happened tomorrow, then most of our scenarios might move in the optimistic McKibben direction.
Okay, next question from the balcony. Since we started late, we're going to let this Q&A period go for another 10 minutes, and I have not forgotten about the folks who RSVP through social media. We'll be announcing the names of people who are going to be going on the nurse tour. But let's start with this gentleman here.
Yeah, actually, this question I'd like to pose to the audience to think about, and it goes to what Max was saying about the movement in this country, the environmental movement in this country being stronger than it is in anywhere in the world. Okay, let me say that with the lead of 350.org, the organization hasn't been mentioned today, but in this country, 350.org, which is an organization that Bill McKibben had a lot to do with, which they certainly deserve a round of applause, is heading up the by far the largest coalition of environmental groups in this country that's ever existed, including a conservative environmental group like the National Resources Defense
I'm gonna have to
Council.
ask, is there a question coming, sir?
There's a question coming. The Sierra Club, I'll be short. The Sierra Club, Greenpeace, all of these organizations are banding together in order to do something about this cause. Credo has got about 50,000 people signed up who are pledging to do something like civil disobedience.
Excuse me.
So my question is
Thank you. Your question is, sir.
My question to the people in this audience is, are you willing as concerned citizens to do something about this with your feet, with your computer, and sign up to join this growing movement which can spread around the world if it happens here first?
Thank you. Okay, do we have another question from the balcony?
Everything we've heard tonight sounds like we need to remove carbon from the air. We've already got too much up there. So I'm part of a group of people who is forming a technical council, and we want to see these established all over the world to evaluate and rank the various technologies that are available right now, such as algae, biochar, scrubbers, you name it. There's about 20 different sectors of technology. My question to all of you is, are you aware of any technical councils, National Academy of Sciences, any standing council that's working on this right now that we can join or we can partner with?
Yeah, there are concerted efforts to look at efforts to mitigate climate change. The one that I would mention is, in fact, the working group, well, an example of one is the working group 3 of the IPCC. And anyone and everyone can comment on that report. It's in the process of being written that deals with strategies for mitigating climate change, both through economic policies and through other strategies. But that's just one of many examples where people are actively investigating both the economics and the science behind mitigation strategies. They have, I think they have issued reports on this, but I'd have to go investigate.
Thank you. We're going to take 3 more questions. We'll start with one here.
Well, climate change is likely to cause famine in poor countries has been widely discussed. But if we continue business as usual, isn't it likely that sooner or later food production will crash in the developed world too, and we starve too?
Yeah. I certainly don't. I'll wait. Okay. I'll wait. Yeah. So that's a really good question. We didn't talk too much about the effect of climate change on agriculture, but it's not just the developing world and that is at risk for food shortages, but rather even this country. And there are some recent papers looking at production of corn, which is a major foodstuff in the United States, and what the impacts of 2 degrees warming would be on food supplies and hence food prices. And the bottom line is that the system is pretty close to optimal right now. And so if you perturb it by increasing it 2 degrees, you can increase the volatility, which means that the risk of a crop failure is much higher. And so right now, this last drought, many corn crops failed. Most of those farmers were insured against that. If that keeps on happening, the price of insurance will go up to the point where it won't be insurable anymore. And I think that the risk of serious impacts on our global food supply are extremely real and serious, and are going to require a lot of thought on how to make what our current system is into something that can be adapted to a much warmer world. Max probably knows more about this than me, though.
No, I think this is a really good point, and I think one important point that we often forget here is that, we think about climate change as an efficiency thing to maximize the size of the pie, but especially when we talk about food, the equity issues really come alive here. So if the price of corn goes up by 5–10%, we on our Berkeley incomes around here, we complain, and bread and steak, and it's all more expensive. But what about the folks that live on $1 or $2 a day, something like that? So these impacts will be felt most by the poorest of the poor. So we shouldn't just always think about maximizing the global welfare, but really looking at the distributional consequences. And these distributional consequences are felt already due to climate change, and they will be more significant going forward.
I would like to just return to the impoverished part of the world, and particularly the Sahel. And there's a beginning program here at Berkeley called OASIS, which stands for Opportunity for Advancing Solutions in the Sahel. And there you have a situation where the population is increasing dramatically because infant mortality is going down, but fertility remains the same. And so there's a problem there anyway. You add climate change on top of that, and there will be food shortages. And my colleague, Malcolm Potts, the head of the Bixby Center, I can quote him as saying, if we don't do something, the major export of that region will be violence. And this is something that we also haven't discussed, but hungry people are angry people. And this is a consequence that I think is very serious and has strategic implications.
Thank you. The next to the last question over here.
Thank you. Hi, I was wondering what portion of the puzzle can be dealt with dealing with deforestation and reforestation, considering that approximately a quarter of the carbon we put in the atmosphere is being absorbed by plants. And I stepped out briefly, so I may have missed it if you addressed it. But are there any worldwide agreements being worked on, to, especially in the third world, to slow down the rate of deforestation, and anything we can plant, not only trees but grasses or fast-growing things like bamboo that can absorb a significant portion of the CO2, or is it just minimal?
Yeah, that's a great question. And something really interesting in Brazil, so I've been working in Brazil for about 20 years, is that if you look at deforestation rates in Brazil over the past 3 or 4 years, they're way lower than they were over the previous decade. They've declined dramatically. And a lot of it has to do with just political forces in Brazil kind of moving in the right direction. I mean, it's also partially due to the fact that, tropical forests are in the limelight much more now than they were 20 or 30 years ago. I mean, when the US had essentially removed the eastern seaboard of forests back in the 1800s, there was nobody crying out for, controlling of deforestation. So, there are some, but then on the other side, there are other tropical countries that still have very high, either absolute or relative deforestation rates. So it looks like things are, overall, Brazil is a big country, a lot of forests. Things are potentially moving in a good direction there. And then, plantations in the tropics, they're extremely productive. So the fastest growing trees in the world right now are eucalyptus plantations in Brazil. And, we use wood. Wood is an important resource in a lot of the things we do. And so if we were a bit more clever about how we allocate land to different production strategies, and even with the use of technology, and it's something that we're going to have to consider as well, is what is the role of technology going to be in a future where there are a lot of people that are starving? And it's something that we should seriously consider. And a lot of times we politicize these issues. A lot of times we radicalize these issues, and we're unwilling to listen to the other side. And we really need to consider what will be the role of technology, what will be the role of different kind of more clever and creative ways to utilize the land.
So I wanted to add a postscript to that. I think there have been some very positive efforts to reforest, and the Amazon is a great example. And some very powerful forces now aligning behind the issue of forest and ecosystem sustainability. So that's a very positive development. The challenge, I think, just for this audience to think about is that the amount of, think about the amount of carbon that's in the entire terrestrial biosphere and compare that to the amount of carbon sitting, as this earlier questioner mentioned, in fossil fuel. There's 4 times as much carbon in fossil fuel waiting to be combusted as there is in all living matter on land. So forests cannot come to the rescue. We're going to have to put a brake on this through much more direct and much more thoughtful and immediate action than hoping that forests will save us, because they can't.
So before we get to our last question, I'm just going to read off a few names here who folks who RSVP'd through social media who are going to be going on a nurse tour. You do not have to be here to attend. Emerson Portillo, Julian Babalev, Luke Scheidler, Sandy Juarez, Gabi Forza, all these lucky people, Jason Wallach, Corabel Silerio, Patricia Hidalgo, and lastly, Michelle Cruz, Anthony Hall, and Siddhartha Cannon. If you're not here, it doesn't matter. We will notify you, but I just want to get this on the record. You will be going on our nurse tour. So last question is going to be up here, this gentleman here. And again, anyone who was unable to actually ask a question here, please leave them on social media. We will respond, definitely. Last question, sir.
Hello. First of all, I want to thank all of you for doing this presentation, for doing excellent, very important science and this important work of outreach. But I still want to ask a tough question. You're preaching to the choir here, you know, both in Berkeley and in California. I think a lot of us here know a lot of the stuff that you're already talking about. How do we get the message out to the rest of the world? How do we get political action galvanized? It seems like you already know what a lot of the answers are. Keep the carbon in the ground where it belongs. As scientists working on this problem, what can you do to amplify the impact of your message, and where does the line between science and politics fall for you personally?
Right through the middle of the Department of Energy was where that line was. No, I'm not going to answer this question. But I will say, you know, we do have, in terms of broadcasting this message, these shows are videotaped and not only posted our own YouTube channels, but to UC TV, University of California Television. And actually the numbers are pretty staggering, hundreds of thousands of views on various shows. So the word is getting out, but beyond that, I'll leave it to our science experts to answer.
I'm looking down at that end of the, yeah. Max?
Well, I guess there's a couple of ways we do this. We do stuff like this, you know, in Berkeley. We do stuff like this in other places that are maybe not as liberal as this audience is. I think some of the things we do, we produce science, and believe it or not, government organizations are full of people with PhDs in various disciplines who are consumers of science, who try and turn this into meaningful policy. So when it comes to something like a new gasoline standard or something like that, that's based on science. When I write a new paper about climate policy or something like that, I write a one-page, non-opinionated summary, and I send it to my friends in the White House and at the EPA and so on. So outreach takes all kinds of forms. A lot of it's informal. Some of it's more formal, like through the IPCC. These assessment reports, we do them for free. Nobody gets paid for them. They take a third of your time. You travel around the world economy class, which is, you know, great and comfortable if you're 6'5". But you spend, you know, 4 or 5 years of your life spending a third of your time summarizing the state of the science in order to get a clean, communicable product that, you know, policymakers and the public can use to see for themselves what the state of the science is. And I think, you know, is this the most efficient way of doing it? I don't know, but it's the best way I know how, and I'm going to keep on doing that. I don't know if anybody wants to add something.
I'll add something to that. You might have noticed that scientists aren't generally comfortable sitting in front of large groups, although this has been a great crowd, and you've made us feel comfortable. But in general, scientists are not generally socially adept. And we're working on this. But I think this is something we have to really impart to our students, that and a young scientist that we interact with, is that the message has to be brought to the general public, and whereas we're probably more comfortable standing in front of a bunch of numbers and charts and graphs and things, trying to translate this message into something that the public can understand and then make informed decisions about is a challenge, and that I remain optimistic that we can train at least the next generation to do a better job than we have.
Did you want to say any closing remark? No.
No, I think Michael left us with much food for thought. I'm going to have to. No, I think I'm good.
Okay, well, that concludes our evening. Thank you, audience. Thank you, scientists. Remember, May 13th, Science at the Theater at the smaller stage, 8 great ideas. Thank you again for coming, and thank you for your patience. I'm sorry about the delayed start.